This is going to be a short video about effective nuclear charge. So what effective nuclear charge is mathematically is it's equal to the atomic number minus the number of inner electrons. What it means conceptually is this. We're going to use the lithium atom over here on our left as an example. So this is a lithium atom. It has 3 protons in the center as well as 3 electrons flowing around the outside. In order to figure out what the effective nuclear charge is, in order to understand it, the first thing you have to understand is that it's the charge that is being felt by the outermost electron. So how much of this nuclear charge within the center is being felt by our outer electrons at the end, or valence electron. So what we can see here is that within this lithium atom, we have 3 protons in the center. We have 2 electrons in the n equals 1 sublevel and 1 electron in the n equals 2 sublevel. So what's happening is these electrons inside are spinning around really fast, and effectively they block some of that 3 positive charge that's coming out of the nucleus from hitting that outermost valence electron. With a charge of plus 3 and 2 shielding electrons, so we say that the inner electrons can be thought of as shielding electrons, they're able to block 2 of the positive charges from the nucleus from reaching that valence electron. Inner electrons are shielding electrons. So as those 2 inner electrons are spinning around and around, they effectively block 2 of the charges. So let's say you have 3 charges trying to get out of the center. Well, 1 would be blocked by that electron, 1 would be blocked by that electron, and only 1 would be felt over here. So that's how you can understand it conceptually. As far as the equation goes, the atomic number of lithium is 3, and the number of inner electrons we can see from the diagram on the left would be 2. So the effective nuclear charge of the lithium atom would just be 1. So this outer electron just feels a net charge of plus 1. If we were to do another atom, let's say we did something a little bit more complicated, we'll go with magnesium. So magnesium has an atomic number of 12. If we're filling the electron orbitals, if we go through the electron configuration, it would be 1s2, 2s2, 2p6, and then 3s2 would complete its electron configuration. So the number of valence electrons are equal to the number of electrons that have the same number as the largest n value. In the case of magnesium, the largest n value you see in the electron configuration is 3. Just give you another example to make sure you understand that. I'm going to over here do another atom. I'm going to do, let's do bromine. So bromine has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3p6, 4s2. I don't have a periodic table in front of me. I'm doing this from memory, so hoping this is right. And 4p5. So bromine, halogen ends in the 4p5 level. So in the case of bromine, which electrons are the valence electrons? Well, again, we look for the highest n value that we have. So for bromine, it would be n equals 4. So that's 4 there. And this over here is 4. So we would say that bromine has 7 valence electrons. It has 2 coming from the 4s level and 5 coming from the 4p level. So it has a total of 7 valence electrons. Well, if bromine has 7 valence electrons, how many inner electrons does it have? The number of inner electrons would just be all the other numbers added up. So 2, 2, 6, that's 10, 12, 18, 28. So bromine would have 28 inner electrons. So the reason I did that really quickly is just to help you understand how to find valence electrons and then inner electrons. So let's go back over here to the magnesium and complete the process. So I'm going to go ahead and draw a picture here. Magnesium has an atomic number of 12, so I'm going to put a 12 plus charge in the center. And then it has 3 energy levels. So those energy levels, let's move this down actually. Need a little bit more room here. So those 3 energy levels would come outside of this, draw these in using a little circle tool. So we might have that as the first one, we might have that as the second one, and out here we might have the third one. For this one, I'm going to use dots to represent the electrons so it doesn't get too confusing. Ooh, let me change that back. Alright, so I'm going to just use dots to represent the electrons. So within the n equals 1 energy level, we can see that within the n equals 1 energy level, we have 2 electrons. So I'm going to represent that with these 2 dots right here. Within the n equals 2 energy level, we have 2, 6, 8 electrons. So we would have 1, 2, 3, 4, 5, 6, 7, 8. I don't know if that was the best color to choose, but I think you can see it there. So we'd have 8 electrons in the n equals 2 energy level. And in the n equals 3 energy level, we have 2. So what is the effective nuclear charge caused by this? Well, the effective nuclear charge from our equation up here we see is the atomic number minus the number of inner electrons. We can see from this diagram that we have 10 inner electrons, and we know the atomic number of magnesium is 12. 12 minus 10 will give us a Z effective of plus 2. 12 minus 10 equals plus 2. Now let's see how that works schematically in the diagram. There are 12 protons in here, so 12 positive charges. So how many are actually able to reach these outer 2? Well, let's say one is blocked by that, another is blocked by that. We get one blocked by that, one blocked by that, one blocked by that, by that. See the idea at this point? They're all blocked. So I can see that of my 12 charges, 10 of them are blocked from being able to reach the far outside and reach my valence. And that's why those valence electrons feel an effective nuclear charge of plus 2.